We are students from the Biomedical Engineering at Surapan Royal Academy. Yeah, and today we are diving into something super cool. But first, have you ever wondered how we can see inside the body without X-ray?
Huh?
Exactly. Think about something like ultrasound, but smarter. Smarter? How?
Oh my god!
Well, imagine mixing lights and sounds together to create clear images inside the body. Light and sound is soft language. It's kind of it. It's called Photoacoustic. You shine a tiny pulse of light into the tissues, and the tissue sends back, believe it or not. Sound wave. No way. Light copying and sound harmony. Yeah. And those sound waves help us to build detailed image of blood vessels, oxygen levels, and even detect early diseases. That's actually amazing. So it's basically light in, sound out, and image. Yeah, exactly. And we are here to show you why photoacoustic is becoming one of the most exciting emerging technologies in modern medicine. Let's get started.
This is Mercury,
Biomedical
and you
imaging
are
plays
currently
a critical
listening
role
of
in modern
biological
healthcare by
processes.
enabling early
However,
diagnosis.
loss
This
syndrome
is
is basically
monitoring and
modality
real-time
tasked in
visualization
continuously
of
verifying
biological
tissue
processes.
nutrition.
However, low
As
single
better resolution
existing
and
modality times
functional or
imaging
molecular
struggle
contrast,
receive
this
visual
unmet need
attention.
has driven the
As better
development of
resolution and
photoacoustic
visual
imaging,
functional or
or
molecular
PAI,
contrast,
a
this
hybrid
unmet
modality that
need
combines
has driven the development of photoacoustic imaging or PAI, a hybrid modality that combines the strengths of optical excitation and acoustic detection.
And
back
here
to
is Photoacoustic
1880.
timeline. Back to
Alexander Graham Bell's discovery.
1880.
He
Alexander
discovered the
Graham Bell's
photoacoustic
discovery.
effect
He
while
discovered
developing
the
the
photoacoustic
photophones,
effect
a
while
device that
developing the
transmits sounds
photophones,
using
a
light.
device
He
that
observed
transmits
that when
sounds
modulated
using light.
sunlight
He
hit
observed
certain
that when
materials,
modulated
they produce
sunlight
audible
hit certain
sounds. The
materials,
phenomenon
they
was
produce audible
first called
sounds. The phenomenon
photophonic
was
effect.
first
It's the
called
foundations of the
photophonic effect.
photoacoustic
It's the
principle. In
foundations of the
1938, early
photoacoustic
gas
principle. In
analysis,
1930,
Emma
early
Wurtzloff
gas
applied the
analysis,
photoacoustic
Emma
effects
Wurtzloff
to
applied
create
the photoacoustic
high-sensitivity gas
effects to
detection
create high
systems in Russia.
sensitivity
His
gas
work
detection
shows that
systems
acoustic
in Russia.
signals generated
His work
from
shows that
absolved light
acoustic
could be
signals
measured
generated from
with remarkable
absolved light
precision.
could be
It's
measured
the first
with
practical
remarkable
engineering
precision. It's the
applications of
first practical
photoacoustic.
engineering
In
applications of
1973, modern PA
photoacoustic. In
spectroscopy,
1973,
Alan
modern PA
Rosenzweig and
spectroscopy.
colleagues developed the
Alan's
modern
Rosenzweig
theories
and
and
colleagues developed the
instrumentations for
modern theories
photoacoustic
and
spectroscopy.
instrumentations for
The work
photoacoustic
made it possible
spectroscopy.
to analyze
The
opaque or
work made
highly
it possible
scattering
to
materials,
analyze opaque or
something
highly
difficult for
scattering
traditional
materials,
optical
something
methods.
difficult
The
for
terms
traditional
of
optical methods.
photoacoustics become
The
widely
terms of
adopted in
photoacoustics
science and
become
engineering.
widely
And
adopted
20
in
years after
science
that,
and
in
engineering.
1993,
And 20 years
researchers
after that,
produced the
in
first clear in
1993,
vivo
researchers
photoacoustic
produced the
image
first
for a
clear in
human
vivo
finger.
photoacoustic
This
image
milestone
for a
demonstrates
human
that
finger.
photoacoustic
This
signals
milestone
could be
demonstrates
detected
that
safely
photoacoustic
and real
signals
levels
could
in
be
living
detected
tissues.
safely
It's
and
the
real
proof of
levels in
concept
living
for
tissues.
biomedical
It's the
imaging.
proof of
In
concept
20th
for
century,
biomedical
Leon Wang
imaging.
and other
In 20th
enabled
century,
photoacoustic
Leon Wang and other
tomography as a
enabled
2D or
photoacoustic
3D imaging
tomography as
technique
a 2D
that
or 3D
demonstrate functional
imaging technique
imagines, including
that
mapping
demonstrate
blood
functional
oxygen
imagines,
saturations
including mapping
using
blood
hemoglobin
oxygen
subsorption spectra.
saturations using
Photoacoustics
hemoglobin
become a
subsorption
powerful
spectra.
biomedical
Photoacoustics become a
emergence
powerful
modality.
biomedical
Increasingly,
emergence
research
modality.
evolved toward
Increasingly,
clinical
research
applications such
evolved
as
toward
breast
clinical
cancer screening,
applications such as
melanoma
breast
detections,
cancer
vascular
screening,
imaging,
melanoma
and
detections,
neural imaging.
vascular
The first
imagings,
now
and
focus
neural
on compact
imaging. The
device,
first now
handheld
focus on
probe, and
compact
integrating
device,
PAI
handheld
with
probe, and
ultrasound.
integrating
Photoacoustics
PAI
moved
with
from laboratory
ultrasound.
demonstrations
Photoacoustics
to
moved from
real-world
laboratory
medical
demonstrations
tools.
to real-world medical tools.
Let's describe the photoacoustic concept. First, a short laser pulse, as a near-infrared light, is directed into the tissue. Second, the light is absorbed by molecules known as chromophores. These molecules convert the absorbed light into heat, causing a very small thermoelastic expansion. That expansion produces ultrasonic waves, which are then detected. Finally, the detected signals are then processed to reconstruct an image that shows the tissue structure and blood oxygenation. Now let's first describe the first step in photoacoustic tomography. Absorption in biological tissues, such as the Beer-Lambert law, describe the intensity of the incident light after a given amount of distance, which can be described by the following equation, which I describe the intensity after a given amount of distance inversely proportional to the absorbed coefficient. The Beer-Lambert law is important in describing the limitations of an optical-based system. In this case, the Beer-Lambert law is used to describe the scattering light by replacing μA with the model scattering constant μs. This equation helps describe the scattering in tissues, where μs is around 1 to 10 millimeters in biological tissues. Scattering coefficient is inversely proportional to the wavelength citation. This means that the major part of incident light has scattered after 1 millimeter. Scattering increases with shorter wavelength. This is why near-infrared (NIR) light is most commonly used in optical biomedical engineering. On the other hand, diffusive optical tomography extends the penetration depth by detecting diffusive photons. This requires complex algorithms and suffers from poor spatial resolution. For biological tissues, to generate high-frequency ultrasonic wave, the incident pulse must be below 1, the thermal relaxation time, and secondly, the stress relaxation time, where dc is the characteristics of dimensions, and the ATH is the thermal diffusivity. Considering a 15 micrometer structure, we can find that thermal relaxation time is 1.4 milliseconds, and the stress relaxation times is orders of magnitude lower than the thermal relaxation time, meaning that the laser pulse needed to be less than 10 nanoseconds to generate high-frequency ultrasounds, which is typical for neodymium doped cantium yttrium doped garnet. Neodymium yttrium garnet lasers that are around 5 nanoseconds in pulse width. Next, I will describe energy absorption. The PA signals at the instant of generation is linearly proportional to the amount of light absorbed. It can be spectroscopically differentiated between endogenous chromophores. As we can see from the graph, different molecules have different absorption. PA uses these properties of absorption to image spatially. In some photoacoustic systems employ an optical permanent oscillators, or OPO, which are nonlinear crystals to create tunable wavelength. To target specific molecules, OPO is used in spectroscopic imaging, which generates two different wavelengths, the signal and idler wavelength. The two wavelengths can be described by this equation, which follows the rule of energy conservation of Planck's law. Given the equation, 1 over lambda pump is equal to 1 over lambda signal plus 1 over lambda idler, which follows the Planck's law E equal to hv. Another thing to consider in an OPO system is the phase. Phase matching follows the rules of momentum conservation. The momentum of light is the sum described as the sum of final light, the idler plus the signal, plus the another constant k, quasi-phase matching, or QPM, which depends on the choosing nonlinear crystals. In bifrequent phase systems, the k-QPM constant will be 0, meaning no momentum loss from phase matching or phase changes, meaning the signal and idler phases are equally 0. which in quasi-phasic crystals, they will contain a QPM constant, meaning that signal and angular wavelength will, after passing an OPO, will have different phases, such as in a PPLN crystal. Data acquisition of PA. The sound attenuation can be described as alpha, where A is the tissue-dependent constant and F is the frequency described in megahertz. B, the biological constant, is around 1 decibel per square centimeter megahertz for most tissues, but 20 decibels per centimeter megahertz for bone tissues, assuming that B, the biological constant, is equal 1. This form of attenuation affects more the higher frequency and thus acts as a low-pass filter, reducing overall resolution for high-frequency PA system. Now, ultrasound detection. First, we'll describe the physioelectric crystal, which occurs when resonance of the wavelength of the generated wave is half-length of the crystal Lt. Physioelectric will generate electricity when there is a sound wave passing through it. The resonant frequency can be extracted with the knowledge of velocity of sound, Ct, which gives the following this equation, which is the resonant frequency. Different type of detector designs of physioelectric systems consist of circular and linear systems, or single detector systems. Now the optical based system. Here we describe a Frober-Prizio interferometer, which create fringes due to the change in cavity length. The path difference from A1 to B can be described as the distance from A1 to A2 plus the distance from A2 to B. As we can see from the image, we can derive that the distance of A2 to B is the cosine of 2 theta. We can then derive the path difference of the wave. This is useful for calculating phases at each location of the Fabry-Prizio interferometer, finding where the node and antinodes are present, describing the emittance of each passes, where n describes the number of passes, T and T palm are the amplitude transmission coefficients at each glass plates, and R is the amplitude reflection coefficient of the glass plates. From entering the mirror structure, the light absorbed from the mirror is a function of T and exited as a function of T palm. Calculating the intensity can be obtained by multiplying the transmitted electric field by its complex conjugate. By shortening the term, R 2R over 1 plus R squared to F, which F is the finesse. The transfer coefficient of Fabry-Prizio interferometer system is simply the transmitted intensity over the initial intensity. This coefficient can be described by 1 over 1 plus finesse plus sine squared delta over 2. The width of the transmitted peak is related to the coefficient of finesse. A method of finding the coefficient involves measuring the width of the transmitted peak. The wavelength criterion states that the separation of corresponding two closely separated wavelengths and must be at least full width half maximum, or FWHM, to be able to be resolvable. For the minimum wavelength difference to be resolvable, the equation gives delta lambda min, which is the minimum wavelength to be resolvable.